welcome back to ISC 4172 Big Data Analytics. Today we're going to talk about data mining, especially how to represent data. So what is data, first of all? Data is simply a collection of entities and attributes. So entities and attributes, those are the terms to call basically the rows and columns of a table. So a row of the table is also called as an object, or sometimes, depending on the context or the authors, people call it entity or sample or instance, data point, or record. Okay, those are all the synonyms of a row of a data table. So let's say you have a database of students. Okay, in that case, a person can be a row of the table or an object of the table. Okay, you can change the scope a little bit, and then you can think about a database of different schools. So how many students are in each school? What kind of demographical composition we can find from each different schools? Imagine we have database of such things. Then in that case, a school can be a row in that data table. Or let's say you're analyzing tweets, analyzing the conversation that's happening on the social media platform. Then in that case, a tweet can be a row of the data table. In the meantime, a column of the table is also known as an attribute or field or feature, parameter, variable code, encoding. There are many, many different ways to call a column of the table. So let's say you have a you have a demographics database. So in that case, a person is going to be each row. So here's Smith, here's Jack, here's Jane. We have different individuals like this, and then for each of the row, we may have the age of those different individuals. Household income can be, another demographical parameter that people might be interested in. BMI can be there as well. And those other variables are basically the columns of a data table, right? So in that case, BMI, age, those kind of things are called the attribute or parameters, variables or fields, those kind of things. Same thing with, again, the school database. Let's say you're interested in, different schools in a school district. So we have school A, school B, and school C. And then for each of the columns, we have the total number of student enrollment, uh, maybe demographical composition of, different schools. I don't know. I cannot think of some immediate examples, but you can imagine what kind of things can go into a school database. So those are all attributes or database parameters. Okay. Now this is a real example of how data sets look like. This is kind of obvious, right? So this thing is something called an Avocado Data Set, which I downloaded from Kaggle.com. Kaggle.com is an open data sharing platform, which we're going to talk about in the next lecture. But Avocado Data Set contains the price of avocados at different locations and different time and date. So each of the rows are basically one observation. Okay. So one day somebody went into a store at some location, and then they measured the price of the avocado, and that's one entry or one object or one data sample. Okay. And then if you look at the column names, we have the date. So that's the date where the price was measured. Average price, I believe this is the average price across a certain region. We have the total volume. This is the total amount of the trades that has happened, in that day. So how many people, how many avocados were sold, on that day, and you can see a lot of different attributes in this data table. So that's basically how usual data sets look like. So nothing really special, but just to make sure that we're using the same vocabulary throughout the semester, I thought it was worthwhile to mention those terminologies. Now, what I want to talk about is different types of databases. So, uh, this is my preferred way of, categorizing different types of data problems. So, we can think of set type data sets. We could also think of sequence type data sets, and then finally space type data sets. So what I mean by that is essentially sets are basically unordered set, literally, So in mathematics, right, when we study the set theory, um, it doesn't, the ordering of the elements doesn't really matter. So a set of 1, 2, and 3, and then a set of, say, 3, 1, and 2, um, they don't really matter, right? The ordering really doesn't matter. So they're essentially the same set, right? So that kind of data is what I consider as set data. Okay, we're gonna see some examples of what exactly those are. Versus the sequence type data, the ordering matters. Okay, so for the sequence type data, and to differentiate them, I'm gonna use just the parentheses. Then for the sequence type data, 1 to 3 is obviously different from 3, 1, 2. Okay, so that's the sequence type data. You can also think of a form of data that has some geometric structure. So, for example, we're up to the US presidential election in November, right? And then you probably see a lot of, those images of, sorry about my bad drawing, but the United States color mapped by the voter preferences, for example, right? So some areas are painted in red, some areas are painted in blue. That kind of data is basically a spatial geometric structured data because the location sometimes really matters. Okay, so another example is the temperature on the Earth's surface. So then you can see the Earth, and then here's America, and then here's Asia, and then you probably have seen this, the figure of the Earth, color mapped by the temperature value, right? So in that case, the geographical location of the value really matters, right? So that is something called a geometrically structured data. Here, I'm gonna just throw out another example. You can also think of a social network data set. So each node here, each circles that I'm drawing, these circles are representative of an individual in a social network. And then if they happen to be, following each other, then I have this connection. So we can imagine this kind of distribution. And again, this is something that has some geometric structure, right? So the connectivity really matters because that's an indicator of who's following whom, right? So you may have some numbers distributed over, those nodes. I don't know what exactly they are. I'm just making up some example, right? And then their geometric structuring of the values really matters. So in some sense, set, sequence, space, that kind of categorization is a categorization based off of the level of ordering. So set is basically there's no order. Order doesn't matter. Whatever collection of numbers, as long as the elements are the same, then we can consider that as a same data entry. Um, Sequence type data set, we're ordering numbers in one dimensional space per se, right? So 1, 2, 3 is different from 3, 1, 2. And then the space type data sets are the ones that has higher than one dimension. So in case of a map or the Earth's temperature or graph structures, those are the data set that has a distribution across. The order distribution across not only just a single dimensional array, but also in two-dimensional or even higher dimensional space. Okay, so that's how I like to categorize different data. So there are lots of examples of unordered data. For example, documents, tweets, web contents. Those are a typical example of unordered data representation. Demographic data, again, it's another example of unordered data. And the reason why I'm telling this is unordered is because, okay, so in one database, let's say I have a student ID, student first name, and then student last name in that order. And then in the other data set, let's say I have student last name first, and then student first name, and then and so on and so forth. It doesn't really matter as long as the corresponding columns match, right? So those are the ones that can be considered as unordered data. Here's another example of unordered data, which is basically documents. So the documents, in case you're not so familiar with the natural language processing, when people analyze, for example, plagiarism, right? So you have two documents, and then what you want to do is to measure the similarity between the documents. And one very conventional way of doing things is basically count different words. So you can count how many times the word, in this example, biotin is referred in one document, and then you can count the frequency of the appearance. You can do the same thing for the other document, and then you can count the appearance of the word biotin in the other document, and then you can compare them together. Of course, if you have only one word, then there's no way to that you can get a correct comparison. But let's say you have now a dictionary of different words, and for each of the words we counted the number of appearance or frequency, right? So then this set of numbers is basically a descriptor of this first article. Okay, and then this data set basically is in each row of this this database is a document or an article, and then each column is basically the frequency of different words. Okay, so that type of data is what is called a bag of words, or BOW. And in case of bag of words, it's an unordered data because as long as you have the corresponding entries, then the ordering itself doesn't really matter, right? Now, order data are a little different. Order data are the ones where the sequence really matters. So you cannot really swap the ordering of the things. The very famous example is a time series. Obviously, you cannot. It doesn't make sense. For example, if you mix up the dates of a stock price movement, right? What else? Sequence type of data. Also, this is some. A lot of times, people just think about time series when we're talking about ordered data, but sequence type data, for example, genetic sequence, DNA sequence. Again, if you mix up the order, then you screw up everything, right? So again, genetic sequence. Genetic sequence is basically an ordering of four different types, right? I'm not neuro expert or anything. So ATGC. Those are the four things, and then depending on how they are repeated, right? In how they are sequenced in someone's gene is basically how their traits are defined, and things like that. So when you're handling genetic sequence, you obviously don't want to mix up the column, right? In case of demographics data, column one be the age, and then column two be the height, or column one be the height, column two be the age. It didn't really matter. But in case of ordered data, it matters because ATGC versus AGTC, makes a lot of difference, right? Same thing, stock price data. So here's an example of stock and price movement. And obviously, if you mess up with the dates, then um, you're screwed. Finally, we get to this geometric or structured data. So this spatial type of data um, are everywhere, in fact, right? So uh, anything that has some geometric or topological or geographical structure, we consider them as space type data or geometric structured data. So spatial temporal data. Those are the ones that, for example, the Earth's surface, right? That's a spatial temporal data. Um, 3D scans. Nowadays, when a self-driving car drives the road, right, it collects, through this thing called a lidar sensor, it collects the real-time 3D geometry of the area, and that's obviously a geometric structured data. So if you mess up the ordering of the points, right, then you basically mess up everything, right? So the ordering, not just in one dimensional order, but in higher dimensional ordering of the numbers become very, very, very important. So again, here's an example of a spatial temporal data. As I mentioned, the Earth's temperature change is basically what people are interested in nowadays in order to understand the dynamics of the weather, the climate change, global warming, those kind of things, right? So to analyze those, scientists collect temperature data at a different geographical locations, and then obviously geographical location matters, right? If you mix up a data sample from Antarctica with I don't know, a sample from Cambodia, then you're gonna just mess everything up. Graph data is another very popular format of data. Here in this example, what I'm showing is what is called a success network in art. It's a brilliant article published in 2018 in the Science magazine, where scientists basically analyze what are the factors that contribute to the success of an artist. So in this particular graph, what they visualized here is the network of the location of exhibitions. So we can see Guggenheim Museum over here. We have MoMA over here. You can see the names of those famous museums and art galleries across the world, right? And then they connected this network of museums and art galleries in terms of you know the exhibition of different artists. So what I'm trying to say is, let's say for example, one artist, let's say artist A, had an exhibition in the MoMA art gallery, and then next year the same artist A had an exhibition in the Guggenheim Museum. Then Guggenheim and MoMA is going to be connected in this graph. So the connectivity basically represent how much of overlap per se in terms of hosting an exhibition of the same artist. Okay, so in social science, this is kind of a really popular type of data because social science by nature is the discipline where people are interested in the connections and networks and how people form a social network, and then how they for example spread information, how those dynamics of spreading the information affects certain things. So obviously graph structured data is very common type of data set, especially nowadays. Here's another similar type of data set. It's a human disease network. So again, it's a network type data that shows which disease has correlation with which other disease. So here's another just a simple example of the graph structured data. Sometimes a data sample, the row itself. So in the previous example, the graph was representing the entire data set, right? But in this example, sometimes a row itself or the entity itself in a data set can be a graph, right? So in this case, what you're seeing here is uh, a pharmaceutical data set. So a molecular structure of a chemical compound is is a row in the table, okay? And then in this particular example, what these people have done was to create an artificial neural network that can predict the efficacy or side effects of a given chemical compound by looking at the molecular structure of that chemical compound. So the molecular structure is represented as a graph form for an obvious reason, right? And then so each of the data entry is basically a graph, which is quite different from those conventional type of data sets. So those are the examples of geometric data set and the structured data set. If you're interested in looking into graph type data sets, snap.stanford.edu is a website that has a collection of a large graph data set. So in case you're interested in, I recommend you to visit there. The reason why I'm kind of emphasizing this is because graph data set is kind of unconventional. I'm pretty sure you're used to those ordered, unordered, and the ordered data sets, right? You've probably seen a lot of tables and Excel sheets, right? At some point in your life, right? But the graph data set, those are the ones that are not, I guess, very common in the daily life, but they are certainly very popular format of data set in many big data problems. So, um, in case you're curious, I recommend you guys to visit the website and then take a look at what kind of interesting data sets are available there. All right, so the last thing I want to mention is, well, there are many different types of data sets, so there has to be an appropriate data representations. So when we talk about data sets, usually data sets come in a few file formats, and the most common type of data formats are CSV files, JSON files, and XML files. So the CSV files, those are the ones that are CSV stands for comma separated values, and those are the ones that are probably the most popular because of its simplicity. So literally, CSV comma separated values, okay, is a text file that has values and numbers split by comma. Okay, so here I am showing an example of a CSV file. You can see that there are a lot of things going on, and then you can see a lot of commas, right? So ID, comma, name, comma, host ID, and so on and so forth. So that's presumably a header, the first row, and then you can see that many numbers here, separated by comma. And if you read that, if you happen to read that, for example, in an Excel program, then what you get to see is this kind of, nice visualization. So basically, what happened when you read a CSV file from Excel is Excel is going to parse this, ugly text, right, based off of the location of the comma, and then it will create this visually, more um, easy to understand type of representation. So now you can see that, different rows, different columns, and then we have the column names, right? So that's basically how the CSV file looked like. And because of simplicity, CSV file, like I said, is the most preferred one. And then parsing CSV is usually very, very simple. You just need to read the entire file as a text file and then just look for the comma and then, split based off of that. Sometimes, some people use something else like semicolon or colon or, whatever. So there's technically no limitations in terms of what you use, which character you use to separate values. But obviously in CSV, comma separated files, comma is obviously the most popular choice. But I do want to mention that in some cases people use semicolon or something else. So sometimes you need to be able to parse the file in a customized way. Okay. One problem, though, I want to mention is that the CSV files are pretty large in file size. If you think about it, it's a plain text. Okay, so if you're not a computer scientist, you may wonder what's wrong with plain text. Well, the problem is the plain text compared to binary is not so computationally efficient. So one character in computer, let's say a character E, okay, or just a number two, right? So if you represent this as a character value, then you're gonna need, depending on your system, it's different, but it's usually 4 bytes, okay, for one character. Now, if you think about it, that's kind of a waste, right? Because, two, if you represent this as a binary, it's only just, 1 O, right? In binary representation. So you only needed 2 bits, whereas now you're using 4 bytes. 4 bytes, 1 byte is 8 bits. So 4 bytes, it means 32 bits. So, each of the numbers here, as well as the plain text, right? Those are actually, one, character is represented by 4 bytes. Okay. Sometimes, some system use 2 bytes, some system use larger, but 4 byte is kind of, a typical, size of a plain text. And if you think about it, because of that, you're kind of wasting your storage. And this is especially problematic if your data size is large, right? Of course, if you have a small table, then, who cares, right? If you have only 100 entries, then you don't really care too much about it. But when you have a large data set, then it may be a little problematic. In the meantime, there's this thing called a JSON data format. JSON stands for JavaScript Object Notation. So JavaScript is a computer language, programming language that is used for developing web applications. So JSON was originally designed for handling of data on the web, for web technologies. So JSON has a format that is easy for humans to read and write, and also it's easy for machines to parse and generate. Okay, so what's on the right is an example of a JSON file format. So as you can see, the curly braces, those are the ones that separates the different object. Okay, and within this object we have a uh, we have an attribute called the first name, we have an attribute called the last name, is alive, age, address, phone numbers, number of children, and the spouse, right? So those are the attributes. And then interesting thing about JSON is that it allows some sort of a hierarchy. So for example, in the address attribute, we have sub attributes called the street address, city, state, postal code. So this is actually quite convenient. Whenever you have a sub attribute, then you just add another, nested, curly braces, and then just, type everything in. Or, as you can see from the phone number, you can have an array of sub attributes. So in that case, array is represented by a square bracket, okay, a pair of square brackets, and then within there we have sub objects, right? And then each of the sub objects has this attribute called type and attribute called number. So in case you have a hierarchical, you know, in case you have a data set that requires a hierarchical ordering, then JSON is probably a good choice, right? Because it allows you to do that kind of thing. Lastly, we have this thing called an extensible markup language, or XML. So XML is, to me, it's actually pretty similar to JSON. I don't find much difference. And as a matter of fact, XML is a little geekier version of JSON. So in case of JSON, you had curly braces to define the object, and then within the object you could have sub objects, things like that. But in case of XML, we have tags. Okay, so root is the how do I say, kind of a default tag that every XML file. Well, yeah, hard to say because XML different people use different standards. So, but root object is an object, okay, and then under the root object we have this object called the listing. So tags are basically are the ones between the angle bracket, and you can consider them as an object. So we have a listing object, and then underneath the listing object, you have a seller info object, you have a payment type object, shipping info object, buyer protection info object, and so on and so forth. Okay. And the objects, in case of JSON, the curly braces were the ones that, define where, the object begins and where the object ends. In case of XML, we just have tags. And start tag is basically, a tag name within angle brackets. And end tag is basically, the same as the start tag, but except that we have a forward slash in front of the tag name. Okay. Sometimes if you have an empty element, then you can use something like this. So let's say in this case, buyer protection info is obviously empty. There's no entry in there. So in that case, an equivalent form would be open angle bracket buyer, buyer protection info, and then space bar forward slash close angle bracket. That's going to be equivalent to this line over here. So it's pretty simple, and as you may have already realized, this is essentially the same as JSON. So there is kind of one-on-one conversion from JSON to XML. Okay. So that's it about some basic vocabularies of data and how they are represented in computers. So instead of actually talking too much about data representation, what are the rows, and those boring stuff, let us just jump directly into an example.